And so now let's up the difficulty. Same concepts, but now let's try out a new chemical equation. Well, in this case, what I see in front of me is an actual statement in English. And what it says is that I had barium hydroxide reacting with iron Roman numeral 3 nitrate. Now notice, how did I know it had to be iron Roman numeral 3? Because I know iron is a transitional metal. It can vary its charge and therefore must have a Roman numeral in the parentheses. So barium hydroxide reacted with iron Roman numeral 3 nitrate to produce barium nitrate and iron 3 hydroxide. Now I can take that a step further because I also have states of matter. So I could say a solution of barium hydroxide reacted with a solution of iron 3 nitrate. And in doing so, it produced a solution of barium nitrate and iron 3 hydroxide as a solid. Now we'll talk about that later on, but I could also say as a precipitate, right? Something that fell out of the solution. But here's what I look at very quickly. It doesn't seem to me as I stare at this equation that everything is balanced. And here's my first little giveaway. I see on the left-hand side 2 hydroxide polyatomic ions. But when I look on the right side, I see 3. So right there, something immediately goes off and I go, I don't think this works. Secondly, when I look at an equation like this, I might be very daunted because, oh my God, look at all those different elements in there and look at all the things I'm going to have to be balancing. So what I'm going to show you is a couple of shortcuts and a couple of ideas that you can use when balancing a chemical equation that may make your life infinitely easier. I usually like to use the following mnemonic device. MENO, as in menochemistry. So what do I mean by this MENO? I'm going to break this down and usually balance things in the following order. Now let me emphasize usually, but this is going to be metals, ions, nonmetals, and then oxygen and hydrogen. Now let me speak into these last two for a second because I know what you're thinking. You're telling yourself, wait a second, aren't hydrogen and oxygen nonmetals? And the answer is they are. But let's just use this as an example real quick. If you notice, oxygen in this scenario seems to pop up all over the place. In other words, every single compound in this particular equation had oxygen as one of its members. So to make our lives easier, what we're going to do is we're going to sit there and we're going to say that let's usually keep oxygen and hydrogen as 2 of the last things we balance. Because oftentimes if we balance everything else that we needed to before we get to them, they will often be resolved by the time we're there. So it's not like you have to do it this way. Nothing that I'm sharing with you is this is the proper way. It's just these are some pro tips that may make your life much easier. So metals, ions, nonmetals, oxygen, and hydrogen. And so let's start with metals. If I look at this chemical equation, I notice that I have 2 metals that are going to be in play, my barium and my irons. So great, let's start by balancing all of them, and this is going to be really easy. 1 barium on the left and 1 barium on the right. 1 iron on the left and 1 iron on the right. This balancing thing, woo, easy peasy. Now I'm going to look at ions. Now, when I say ions, what I really mean are polyatomic ions. Now, why do I want to use that instead of nonmetals? So let me show you something. I could look at this first compound of barium hydroxide, and I could say correctly that in this compound of barium hydroxide, I currently have 2 oxygens. Why? Because I had 1 oxygen in here. 1 times 2 is going to be a total of 2, right? Now I could do that. There's nothing wrong with it. But the reason why this may get very convoluted very quickly is that now I'm going to sit there. Oops, I'm putting that in the wrong spot. Now I'm going to sit there, and when I'm going to try to balance all of my oxygens, I'm going to have to do the same trick over here. So let's take a look at this compound. In this one, how many oxygens are there? Now, if I lose my mind, I might look at that real quick and go 3 or 6. But in reality, remember, it's 3 times 3, so I actually have 9 oxygens on this one. So look at how this can start to get a little annoying. I had 2 over here, and I had 9 over here. But then I come over to the right side, and what I'm going to start to see is that, well, I'm going to have to keep track of all of this because this is going to be continuing on as I move forward. And one of the first things I'm going to notice is that over here on the on the right-hand side is that I have 6 oxygens in this one, and over here I only have 3. Ruh-roh! 11 does not equal 9. But now the million-dollar question is, so of those 4, who should I put a coefficient in front of? And the answer is, I don't know. Because this is hard. And this is tricky. I can't figure out, just by looking at this, where exactly I should put it. So instead, let's not worry about the nonmetals for now. Because what I'm going to do instead is I'm going to look at this closely, and I'm going to go, hey, wait a second. I see that the hydroxide I have over here was the exact same hydroxide I had over there. Ooh, I also see that the nitrate that I have here is the same exact nitrate that I had over there. So if the ion stays together, then let's make our lives simple and let's count the ions. This is going to be a heck of a lot easier than breaking it down into individual elements. Now, what I mean by that is that right now here I have 2 hydroxides, over here I have 3. Ruh-roh! Now 2 and 3 is not going to be an easy thing to just get to, so instead I'm going to multiply by the least common multiple. The least common multiple between 2 and 3 is going to be 6. So that means that I'm going to need 3 of these and 2 of those. So let's take a look and see what happened with my hydroxides. So I had over here on the left-hand side 2 times 3 gives me 6 hydroxides. Awesome. 6 hydroxides on the left. And now I look over here on the right, and I have 2 times 3, 6 hydroxides. Woohoo! Life is good. Hydroxides balanced. But, ruh-roh, who did we mess up when I added that? Well, it looks like I messed up both the barium and the iron. But that's okay. This is a quick fix. I can put a 3 here. There's my 3 barium nitrates. I can put a 2 there. There are my 2 irons. So now, 3 bariums, 3 bariums. I have 2 irons, 2 irons. I have 6 hydroxides, I have 6 hydroxides. So let's check in on that last one, the nitrate. And what I notice is I have 3 nitrates here, so there's 3 nitrates there in total, times 2 is 6, and over here I have 2 nitrates, times 3 is 6, and ta-da, this is now a balanced chemical reaction. And so to practice one last type of balancing and give you the last little pro tip that I have here is let's take a look at a combustion problem in which students can often get stuck into this loop where you start to repeat over and over and over and it's not clear how to get out of it. So what we're going to do is that in this combustion reaction that we'll learn more about later on, we're going to have propanol, that's going to be the C3H7OH, reacting with oxygen, and it's going to produce carbon dioxide gas and water vapor. And so we're going to start this the exact same way. Again, I'm going to start by doing my MENO, right? And so I'm going to sit there, I'm going to say, okay, so I have metals, ions, nonmetals, oxygen, and hydrogen. I'm going to start by, since there's no metals, there's no ions, I'm going to start with my nonmetals, and in this case, it looks like carbon is going to be the easiest one to go after. So I sit there and I look and I see I have 3 carbons on the left here, and so I'm going to go ahead and stick a 3 there. So now there's my 3 carbons. Now I look at my oxygens. Ooh, I have oxygens everywhere. You know what? Instead of doing it this way, I'm going to, for a moment, rewrite this and say that MinHo chemistry. And it's the same thing. Why? Because if I find that hydrogen pops in less places than oxygen, that's probably the easier of the two to balance. So let's go after that one. Let's not reinvent the wheel and go crazy. So what I'm going to do is I look at the hydrogens and I look closely. I have 8 hydrogens on the left. Why 8? 7, right, plus the 1. So I have to put those two together. So 8 on the left. And then I'll look over here, and here I'm woefully deficient, so I need a 4 in front. So 8 on the left, 8 on the right. Everything so far, so good. But this is where the trap happens. This is where we have to be careful. So the last one I'm going to go balance is my oxygen. Now, obviously, I'm going to have way too few over here on the left-hand side. I literally have 1 there and I have 2 there, so I'm short. So let's see the total number of oxygens that I have on the right. So I have 3 times 2, which is 6. 6 plus 4 times 1, so 6 plus 4. So that gives me a total of 10 oxygens on the right-hand side. Now, why is this sometimes challenging? What students will do is that they'll come over here to the left-hand side and they'll sit there and they'll be like, okay, so I need 10. That means I need to put a 5 in front of that. Ruh-roh! They ran over something. And what they ran over was that there was an oxygen sitting over here. See, here's the paradox that we're going to run into. This is what I call the even-odd dilemma. And the reason why it's a dilemma is because whatever number I put in front of this oxygen here, the fact that I have a 1 over on the left will always make this value on the left-hand side odd. And there's no way for me to make an odd equal an even. Got it? So there's nothing that I can do by adding or taking away to this oxygen that's going to resolve this issue. So when I run into this problem, the easiest thing to do, as soon as you identify and you're like, I think I'm in an even-odd dilemma, is watch this. Double everyone. What do I mean by that? Well, I'm just going to go ahead and put a 2 there. And I'm going to make this, instead of a 3, I'll scratch it out so you see it, I'm going to make this a 6. And instead of this a 4, I'm going to scratch this out and I'm going to make this an 8. Now watch what happens. Notice I left this guy still blank, but I basically doubled all of my reaction with the exception of the oxygen on the left. And so what I'm going to do is that let's just figure out real quick, well, how many oxygens do I now have on the right-hand side? 6 times 2 is 12. 12 plus 8 is 20. No surprise, I basically just doubled the amount that I had on the right. But now notice, because I put this 2 here in front of the propanol, I've now made this an even value. So no matter what I put here in front of this oxygen, I can put an odd number or an even number. I'll always produce an even number, and aha, even will equal even. So when I put a 9 in front of this guy, now suddenly I have 20 hydrogens equaling 20 hydrogens, and my reaction is balanced. So the easy way to approach this is whenever you're stuck in this even-odd dilemma is go ahead and double the reaction. That way usually the numbers will start to work out a lot better. If you don't like that, there is another possibility. And the other possibility, let me go back to where we were. So I had 3 of these, I had 4 of those. The other possibility is that because these are coefficients, they don't have to be whole numbers. Now, let's take a beat on that. So normally we say that I need 1, 2, 3, 4, 5 oxygen molecules. Well, what happens if I had 1.5 oxygen molecules? Well, then really what you're saying is that you had an oxygen molecule, see it, plus, in essence, half of another one, or you had 3 oxygens. Now, you may use decimals or fractions if that is more readily accessible to you. If you like that and you find that to be easier, then go nuts. So what does that mean? When I got to this point where I had 3 carbons, I had 8 hydrogens, and now I'm sitting over here on this side with my 10 oxygens. Well, I know that I'm going to get 1 oxygen from this. So 1 plus, in essence, 2x equals 10. That's where we're at. And so when I go ahead and I solve this, I'm going to find that 2x equals 9, or x equals 4.5. And you could put a 4.5 right there, or 4.5, same tomato, or 9 over 2, same thing. But when you do this, what happens is that you will still produce the same balanced chemical equation. In essence, what you've done is now you're telling me 4.5 times 2 is 9, 9 plus 1 is 10. And so it still balances and it still works out. This is no different than if you just would have multiplied every one by 2. That way you're not stuck with a fraction or a decimal as a coefficient. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.